So thanks a lot. And then the second talk in this session is actually an invited talk. So it's our pleasure to have Stacey Jeffery here from CWI and QSoft. And actually, she's also a co-founder of Women in Quantum Development, which I think is a great initiative. So we are very happy that you could also come here. And the title of your talk is Quantum Walk Search Algorithms, which is, of course, a very nice and broad topic, deep topic in our field. So thanks a lot for accepting our invitation. And please, the stage is yours, Stacey.
Thanks a lot. And thanks for inviting me to give a talk at this nice event. So I'm Stacey Jeffery, and as Zoltan said, I work at CWI, and I'm also affiliated with QSoft, which is the Dutch research center for quantum software, which includes applications of quantum computers. And in particular, I work on designing quantum algorithms. And a lot of my work is on an area of quantum algorithms called quantum walks. And one nice thing about quantum walk algorithms is that there are these tools that can be used to design new quantum algorithms based on classical algorithms, classical random walk algorithms. So this is you could say it's a particularly easy way of designing quantum algorithms where you can use a lot of classical intuition. So in my talk, I'm going to discuss some of these tools, and well, I won't even have to talk about really like the low-level details of the quantum algorithms themselves. And these are tools that you could already take and start designing your own quantum algorithms. So to start off, there are two algorithms that came out in the mid-90s that could be credited with getting the wider computer science world interested in quantum computing. And one is Shor's algorithm for factoring, and the other is Grover's quantum algorithm for black box search. So briefly, if you're given black box access to some function f, whose outputs are 0 and 1, meaning you have no information about the function, but you can ask for any x, what is the value of f of x, then a classical procedure would need basically to query everything in x if you want to find some x such that f of x is 1. So if you want to be able to find such an x with, say, at least constant probability, then you'd have to query like a large fraction of the possible inputs in x. And that's at least sort of in the worst case where there might only be 1 or 2 values x such that f of x is 1. And that's because the only thing you can do with f is query some x to learn f of x, and you can do this for different values of x, but there's nothing you can really do besides this. You have no other information about f. And so you essentially just, all you can do is query random values or query values in order. It doesn't really help. Whereas we know that if you have if you're able to query this function in superposition, then there's a quantum algorithm that solves this, only evaluating the function like square root of the size of x times. And while this only gives you a square root to speed up, this is a really important algorithm because a generalization of this algorithm can essentially speed up any classical brute force search algorithm. And brute force search comes up a lot, so this technique can be really widely applied. And that's actually one main reason that it's interesting to study this weirdly phrased black box search problem, where you're given some f that you can evaluate like a black box, and you want to find an input that evaluates to 1. Like, why would you want to do that, right? In practice, you're never actually given a literal black box. When you're searching for something, you almost always know something about what you're looking for. Usually you have some structure in the problem that you're trying to solve. But the thing is, in practice, in many, many contexts, we have absolutely no idea how to make use of any structure of the problem when we're trying to solve it. And so the best thing we know how to do for many problems is to treat them as black box search problems. And if that's the best you can do classically, then quantum gives you a quadratic speedup using this technique. Okay, but sometimes you're searching for a solution and you do know a bit more structure of the space that you're searching. And we might ask, can quantum help in that setting? And to partly answer this question, we can look at another type of classical search process, which is random walk search. So here's a map of Amsterdam, which is where I live. And if you ever find yourself in the center of Amsterdam or any other city with no map, dead phone battery, and you're too stubborn to ask for directions, then you may know from experience there's really only one strategy for finding your way home or back to your hotel or wherever you're going, which is to pick a random direction and just walk to the next intersection. And once you're there, choose another random direction. And you repeat until, eventually you will find your home or hotel this way. And the technical term for this process is a drunkard's walk. This type of strategy is used widely in algorithm design, particularly for problems where we don't have a metaphorical map. In other words, you don't have a very clever way of finding a solution. The problem doesn't seem to have a useful structure that you can exploit, but you have some way of randomly drifting through the space of solutions. And this happens quite often for many problems. But then, of course, an important question is, how long does it take you? How many steps of random wandering before you can expect to have found your way home or a solution to your problem? And this depends on the graph that you're walking on, and it depends on the location of the X of the thing that you're looking for. But generally, this is a quantity called the hitting time. And for many search problems, the best known algorithm can be modeled as random walking on a graph, and then analyzing the hitting time gives an upper bound on the complexity of the algorithm. So an important question, in light of the fact that we can speed up totally unstructured black box search quadratically, is, can quantum computers speed up random walk search algorithms where we have a little more structure, and by how much? And we know some answers to this question, and this is what I want to talk more about today. So first, to get everyone on the same page, I'll talk more about precisely what I mean by brute force search and how we can speed that up with a quantum computer. And I'm not going to talk about any algorithms in detail, because again, the beauty of these techniques is that you don't actually need to think about the quantum algorithmic details. These tools allow you to just take classical search algorithms and somewhat generically speed them up. And then I'll talk about random walk search algorithms and the techniques we have for speeding them up with quantum computers. Okay, so to get started, let's review what I mean by brute force search, which is just a type of classical algorithm. Brute force search can solve any search problem, and a problem is a search problem if the input somehow specifies a marked set M, which is a subset of some known set omega. And the goal is to find some element U that is in M, or we could say some element U that is marked. So for example, if we consider the problem of collision finding, this is a search problem on pairs of n-bit strings, and the input is some function H that takes an n-bit string and outputs some m-bit string. And we want to find a collision in this function, meaning we want to find a pair of X and Y such that X and Y are distinct, but H of X equals H of Y. This is a problem that is important in cryptanalysis, for example. This is one example of a search problem. Finding an integer that is a non-trivial factor of some input integer is another example of a search problem, but there are many, many examples of problems of this type. So abstractly, something is a search problem really if you're given the input, there's some notion of marked, and we have a way of checking for any U if U is marked. So we can sort of see the input itself as defining some subroutine that takes a U and checks if U is marked. And of course, it's hard to imagine solving a search problem if you don't have such a subroutine, if you can't even recognize the thing that you're looking for. And of course, we need one more subroutine to have any hope of solving a search problem. And that is, if we can't even find things in omega, so things that might have the possibility of being marked, then of course we can't hope to find things that are marked. So we do need a way of sampling potentially marked things. But yeah, and in all of our examples, the sample will be uniform, but that of course also need not be the case. We do of course require that when you sample, there's some non-zero probability of sampling something marked, because otherwise, of course, it's not at all clear how you could possibly solve this problem. So these are sort of the minimum subroutines that you would need to possibly have any hope of solving a search problem. And given these, there's always a way to solve the search problem, which is by brute force search. So basically, you can always solve a search problem by just sampling and then checking if the sampled thing is marked, and then repeat. And if epsilon is some lower bound on the probability that one sample is marked, then you have to repeat this process about 1 over epsilon times. And so then, you know, the complexity, if C is the complexity of your checking subroutine and S is the complexity of your sampling subroutine, then your brute force algorithm has complexity 1 over epsilon times S plus C. And we know by the sort of quantum search or amplitude amplification, as it's called, framework, that given this setting, there's a quantum algorithm that is even faster. So if we have a quantum algorithm with access to these 2 subroutines, then you know, you can solve the search problem with complexity like 1 over the square root of epsilon times S plus C. And I'm not going to tell you what this algorithm looks like. That's beyond the scope of my talk, but you know, given like this, the fact that this quantum algorithm exists means that you know, you can sort of, without really understanding the details of the algorithm, you could already design some quantum search algorithm, and you can already know that you can speed up these sort of classical brute force search algorithms. Now, there are a few details that I'm glossing over. For example, you know, for many of the algorithms I will talk about, it's not enough to be able to sample. You actually need what's called a coherent quantum sample, but it's often the case that these 2 things are equivalent. So I will, for details, I'll refer you to the references that I'm going to be putting up on my final slide. So again, I want to emphasize what a really useful tool this is, because, you know, well, hopefully you know that quantum computers can't just speed up any classical algorithm in general. If that were the case, you know, I wouldn't have a job as a quantum algorithms designer. So when we find a very special type of classical algorithm like brute force search, where we can get a generic speed up, that's extremely useful. Okay, so let's look at an example of a brute force search algorithm for the collision finding problem. So remember, the input is some function h, some perhaps hash function, and we want to find a pair x, y, such that h of x equals h of y. And so the cost to sample a uniform pair is, you know, going to be polynomial in n. And similarly, the cost to check if a pair xy is marked, meaning that x and y are not equal and h of x equals h of y, should also be polynomial. That's assuming that we have some efficient way of evaluating h, which is usually the case. And then we need to consider the probability that a sampled pair xy is marked. And this depends on the function h, but often in the setting of collision finding, h is some many to one function. So we could assume, for example, that it's at least 2 to 1. Then a pair is marked with probability 1 over 2 to the n. And that's because in a 2 to 1 function, every x has something that it collides with. So, you know, for any x, there is some y such that xy is marked. And so a sample is marked with probability 1 over 2 to the n. And so if we combine all of these things, we get a classical algorithm that solves collision finding in like about 2 to the n time, or a quantum algorithm that solves it in 2 to the n over 2. But you may be very unimpressed with this because this is not a very good classical algorithm for this problem. And in fact, there's actually a more clever classical algorithm that only uses 2 to the n over 2 times. So we don't need a quantum algorithm to do that. So now let's look at a more clever quantum algorithm that does even better than this, but also using this kind of quantum search. We're going to begin with a pre-processing step where we initialize a list and add t things of the form x h of x. And we're going to sort them, we're going to insert them into some nice data structure so that they're sorted by their h of x value. That means that already if there's a collision within two things within this table, if two things in the table collide, we'll already detect that because they'll end up being kind of beside each other in sorted order. But as long as t is not too large, then with high probability, we will not have already found a collision. And so the second step is going to be a brute force search, where we're going to sample a uniform new value y outside of the table L, and we're going to check if y collides with anything in the table. And so the complexity of the sampling is like polynomial in n, and the complexity of checking if y collides with something in the table is also polynomial in n. We're going to kind of just do a lookup, one sort of table lookup. And so the complexity of the second step, let's first consider the classical complexity. So the probability, if we sort of choose any, if we choose a random point outside of our table, what is the probability that it collides with something in the table? Well, since we're assuming that h is a 2-to-1 function, each of these points in the table collides with something. So there's t good things that we could choose. And so the probability that we choose one of the good things, one of the things that collides with the table, is like t over 2 to the n. And so if we plug these three values into our classical expression, we get that this search part has complexity like 2 to the n over t. And if we add the complexity of part 1 and part 2, we get this expression. So setting t to be 2 to the n over 2 gives us a classical algorithm with complexity 2 to the n over 2. And actually, I'll say this is not a very interesting classical algorithm, because what we would actually find is that if we take t to be 2 to the n over 2, then we already with high probability just have a collision in our initial table, and we don't need to search for something that collides with it. However, if we instead use a quantum search in the second step, then we will plug these three values into our quantum formula, which has a square root. Then we see that the complexity of the second step is square root of 2 to the n over t. And if we add these two things, we get that by setting t to be 2 to the n over 3, we get a quantum algorithm for collision finding with complexity 2 to the n over 3, which is in fact optimal for this problem. Okay, so this is some examples of quantum search. And now let's look at a search technique that is less brute force and more drunken wandering, which is random walk search. And the canonical example of a random walk is the person I mentioned earlier, randomly wandering around an unknown city. And the key feature of this example is that we implicitly assume that the walker is local. That is, she does not have a map. So at any given time, the walker only has local information about her immediate surroundings. And when she makes a move to a new location, she forgets where she was. And now she only has local information about the new intersection. And this is what really characterizes the random walk setting. And many algorithms follow such a pattern of random wandering. So let's consider a more concrete example. Suppose we have a formula phi. So the inputs to the formula are binary strings, and we'll assume that it's a product of some simpler formulas called clauses. That's the C1, C2, C3, that each just depend on a small number of bits. And the goal is to find a string x such that phi of x is 1. So this is a search problem, and it's not really clear how to solve the search problem. So what you might do is just try a random string. And if so you choose a random x. If phi of x is 1, then you're done. So suppose that phi of x is 0. And now you should try another string. But you can get a new string by actually just changing x slightly. So you could just change a single bit of x, for example, to get a new string. And this might also make it easier to compute phi of x, because you only have to recompute the clauses that depend on the bit that you changed. And, if you continue in this way, it might take a very long time, but eventually you will find a satisfying assignment, assuming that one exists. And many algorithms have this structure, and abstractly we view them as a random walk on a graph, where the vertices of the graph represent all the candidate solutions to the problem. So in the example of satisfiability, the vertices of the graph should be all the binary strings of the right length for our formula. And then there's an edge or a line between any pair of vertices if we want to consider transitions between them. So again, in the example I just mentioned, two vertices have an edge between them if they represent strings that differ in a single bit. And you can see the example here for n equals 3. This is called, this particular graph is called a hypercube. So a random walk search algorithm works by just starting from a random vertex and then moving along the graph randomly until it finally lands on a marked vertex, where we say a vertex is marked if it has, if it somehow encodes the property that we're looking for. Like in this case, if it's a satisfying assignment, and we'll sometimes color these vertices red. So, okay, more generally, a random walk on an undirected graph is a type of Markov process, and it models a walker on a graph who at every step moves to a neighboring vertex at random. And it's also possible to have weights on the edges so that some edges have a higher probability of being taken, but in this talk, all edges will just have weight 1. And mathematically, a random walk can be described by a transition matrix, P, that's indexed by pairs of vertices, where P UV is the probability of moving to V when you're at U. So it's 0 if U and V are not actually connected by an edge, and it's 1 over the degree of U if U and V are connected by an edge. And as long as the graph is not bipartite, a walker starting anywhere will eventually approach a distribution called the stationary distribution, which I'll denote by pi. And in the unweighted case, the stationary distribution is just proportional to the degrees of the vertices in the graph. And this distribution is also the unique one eigenvector of the matrix P. So notice this means that a walker who's in the distribution pi will also be in the distribution pi after one step of the walk. So pi is the limiting distribution of P. A walker is always moving towards this distribution, and if a walker is in the distribution pi, she stays there. And so then a very natural question is how long it takes a walker to spread over the graph until she's approximately distributed according to pi, this limiting distribution. And this is well approximated. This is called the mixing time, and it's well approximated by a quantity 1 over delta, where delta is the spectral gap of the transition matrix P. So importantly, this 1 over delta, after 1 over delta steps, starting from any distribution row, the walker will be approximately distributed as pi. So random walk algorithms, these are often a useful way of modeling more clever search algorithms, where instead of just sampling uniform objects at each step, you have some more clever way of moving through the search space. And so we begin somewhere on the graph, sampled at random. And for that, you need a subroutine that samples vertices of the graph. And then you move to a random neighbor of the current vertex, which we call an update. And this is accomplished by some subroutine, the update subroutine. And what this has to do is, we have this matrix P whose uth row describes a distribution over the neighbors of U. And so whenever you're at the vertex U, the update has to select a new vertex from this distribution. So it basically selects a neighboring vertex at random. So given all of the neighbors, one of them will be selected and the walker will move to that vertex. Then, of course, we have to check if the current vertex is marked. And, if for that, we need some checking subroutine. And if not, we repeat. And so basically, we're just wandering around on this graph at random, hoping that we run into a marked vertex. And an important question is, how long will this process take, or how big does T have to be so that we can expect that we will find a marked vertex within T time steps? And this depends on the structure of the graph and also the number and location of marked vertices, but generally this quantity is called the hitting time. So for a given random walk P and a marked set M, that's a subset of the vertices of the walk, the hitting time is the expected number of steps needed to get to a marked vertex, in particular when you start from this stationary distribution pi of P. And so, as I mentioned, the hitting time depends on which vertices are marked. For example, if there are many marked vertices, then it's probably easier to find one. But in some graphs, it also may be more or less difficult to find a marked vertex. So, for example, if the graph has some very unlikely to reach area and the marked vertex is there, then the hitting time may be very high. So generally, the hitting time depends on the graph and the marked set, but in many cases, there are techniques that can be used to upper bound it, and this gives you an upper bound on the number of steps that an algorithm of the form I just described would need. So this is that algorithm again. So if we run our random walk algorithm now for HT steps, where HT is the hitting time, then it will find a marked vertex with high probability. So this gives a classical algorithm for finding a marked vertex that runs in time S plus the hitting time times U plus C, where S, U, and C are the costs of these subroutines, sampling, update, and checking. And one reason this is very interesting for us is that given such a classical algorithm, there is a quantum algorithm that does better, finding a marked vertex in this expression, where now we have a square root over the hitting time. So let's compare this with our quantum algorithm for brute force search. And for comparison, I want to note that the hitting time is always at least 1 over epsilon and at most 1 over epsilon delta. To see that the hitting time is at least 1 over epsilon, you can note that since we start in the stationary distribution, we are in the stationary distribution at each step of the walk. So at each step, individually, the probability of being marked is epsilon. Now, these different steps are not independent, but this lower bound still follows from the union bound. On the other hand, we have an upper bound of 1 over epsilon times 1 over delta, and that's because remember that after 1 over delta steps, 1 over delta is approximating the mixing time. So after 1 over delta steps, you have a new independent sample from pi. And so you only need 1 over epsilon of these like 1 over delta step repetitions before you have seen 1 over epsilon samples from pi, and with high probability, one of them will be marked. Okay, so the hitting time is always at least 1 over epsilon, but this quantum walk approach can do better than brute force search because it's often the case that the update, the cost to do an update is much smaller than the cost to sample, so that you can often be much smaller than S. Basically, this is because moving to one object, from one object to a nearby object is often easier than sampling a completely fresh random object from scratch. And let's see this with an example. We're going to consider the problem of element distinctness, which is essentially the same as the collision finding, except the major difference is that we will not assume that there are many collisions. So in the element distinctness problem, there may be as few as a single collision. That's the worst case, and that's what we'll actually consider. The worst case is where M just has a single pair AB. I guess also BA would also then be a collision. So if we consider our previous collision finding approach to this problem, where we make a list of T x f of x pairs for T random values of x, and then we search for something that collides with our list, actually this will not succeed with very high probability, because the only way we'll succeed is if our list L happens to have part of a collision. But if there's only one collision AB, this will only succeed if A or B is in the list L. And that will happen only with small probability. And so what we're going to do is we're going to modify this algorithm so that now we will search for a list L that contains part of the collision. So we'll sample a list L of T pairs, and it's not necessarily going to be a good list, meaning a list that contains one of A or B, but we'll check if it's a good list by searching for a y that collides with something in the list. So we won't always succeed in this search. When we don't succeed, that will mean that we didn't have a good sample here and we need to sample again. So the cost of sampling a list is approximately t. Now I'm just ignoring polynomial poly n factors. The cost of checking is going to be, well, this checking is now a search. So when we sample something outside of the list, what is the probability that it collides with something in the list? Well, assuming A or B is in the list, there's only one unique item shown here in red that would be a good item to sample. And so the probability that we sample the good item is 1 over 2 to the n. And so we get, if we use quantum search, we can find the good item in square root of 2 to the n cost. And so then, okay, what is the probability that our sample was a good sample? Well, a good sample is one that contains part of the collision. And in the worst case, there's only one single collision. So the probability that we get part of it is like t over 2 to the n, or maybe 2 times t over 2 to the n, since there's two values A and B that need to be in the list for it to be good. So if we plug this S, C, and epsilon into our formula for quantum search, we get this. And you can see that if we set t to be 2 to the n over 2, then this gives us an algorithm for element distinctness that takes like 2 to the 3n over 4. This is not a bad algorithm. A classical algorithm for this element distinctness problem would require like 2 to the n. So this is a speed up, but we haven't used the quantum walk technique, and we can do even better. Because here there is a major inefficiency, which is that we are repeatedly making a fresh new list L, which is expensive. Every time we sort of refresh this list, we have to like choose and query t new elements, and this is expensive. And so we'll find that in our quantum walk algorithm, we're going to save by only doing this sampling once. So let's see how a random walk algorithm, which we can later quantize, could solve this problem. So we're going to walk on a graph where the vertices are all of the different possible lists L of size t. So we will see these are sets of t x f of x pairs, but equivalently we could sort of consider the vertices by being labeled by all of the sets of t n-bit strings. And two vertices will have an edge between them if they're almost the same, but they differ in just a single element. So that is in one step of the random walk. This would just involve, removing an element and adding a new one. So here we get, we take one step of the walk from here to here. We just remove this green ball and we add the yellow ball. And the graph that we're walking on that is described in this way is a very well-studied graph called a Johnson graph. And it's very useful to work with well-studied graphs. We'll consider a vertex to be marked if it contains a part of a collision. So, if there's something in the set that collides with something outside of the set. So in our example, we have, there are 2 red balls in our input. And so any set containing a red ball is marked. Okay, so then we're going to be doing a random walk where we walk until we find such a set. So we're interested in how many steps we need, or the hitting time. And in this case, the hitting time is approximately 2 to the n. And one way you can see this is that in 2 to the n steps, you're basically going to see 2 to the n different points, x, f of x, which is sort of sufficient to have a constant probability of seeing one of the, red balls, one of the parts of a collision. Okay, so then we need some subroutines to make our random walk algorithm work. First, we need to be able to sample an initial vertex. So we need to be able to sample a list of t x f of x pairs. And this is going to cost approximately t. And then we need an update. So we need a way to transition, which means we need to be able to select something in L at random, remove it, and then insert a new x f of x pair. And this is like, this costs like something that's like logarithmic in n, which I'm calling 1 because I'm ignoring, this is rather logarithmic in 2 to the n. So this is something that costs like n, and I'm ignoring poly n factors. So I will just call this 1. And then finally, we need a way to check if a list is marked. And remember, a list is marked if it contains part of a collision. So the way we will check if it marks is we'll search for something that collides with our table. And as we saw before, the cost of that is like square root of 2 to the n using quantum search. Okay, so then if we plug all of these values, hitting time, S, U, and C into our formula, we find that, we get a complexity of t plus 2 to the n, and this is not good at all. It's worse than the algorithm we saw before. And also notice that it doesn't matter what we take t to be, because this algorithm doesn't do any better than a classical algorithm that just sorts all 2 to the n points x f of x by their f of x value. So this is actually not a good algorithm. And there are 2 ways to address this problem to make a better algorithm. That's actually even optimal. The first is we can change what it means for a vertex to be marked. So let's look at that solution first. So now we've changed the definition of what makes a vertex marked. And now for a vertex to be marked, we'll require that it contain both halves of the collision. So, looking at our example in pictures, that means that a vertex will be marked if it contains both red balls, not just one of the red balls. And then the trade-off is there are far fewer marked vertices now, so the hitting time will be larger. So now the hitting time is going to be like 2 to the 2n over t. And the intuition is that it takes t steps to almost completely replace L. So after this many steps, we've seen 2 to the 2n over t squared independent sets of size t, which is the inverse of the probability that a random set contains the collision. But basically, the intuition is that, now there are sort of, now our requirement for being marked is kind of more stringent, which means that there are fewer marked things. It's harder to find something marked, and so the hitting time is higher. But the checking cost now has gone down. So now we can actually check in constant time, because we can basically just, every time we insert a new element into our set, we can kind of make a note of whether, because things are being inserted in sorted order. So we'll see a collision immediately, and we can just make a note that there is a collision somewhere here. So we always know if we have a collision. We don't have to do any extra queries to check if we have a collision. And so the checking cost now is very small. And so if we plug all of these things into our formula, then we get an algorithm where if we set t to be the optimal value of 2 to the 2n over 3, then we get a quantum algorithm for element distinctness with complexity 2 to the 2n over 3, which is optimal. So this is better than we could possibly do on a classical computer, and it's optimal for a quantum computer. And I mentioned, so this is one way of sort of fixing the approach that we did before. And again, I want to sort of draw your attention to the fact that this expensive sampling that costs t, we only do it once. We don't have any sort of factor in front of it. But I mentioned that there would have been one other way to fix the bad algorithm we saw before. And it motivates the next type of quantum walk technique that I want to present. So remember, in our first attempt at this problem, we were unsuccessful because the cost of checking if a vertex was marked was so high. And we found a way to reduce this cost. In this what I've just shown you, we found a way to reduce the checking cost. But there's another solution, which would be just not to check so often. And if you think about it from the standpoint of a classical random walk, every time you replace an element in the set, you're searching to see if it forms a collision with anything outside the set. But this is a huge waste, because if instead you only check every t steps, then you'll basically just be checking only when the set is completely renewed. And this will turn out to help a lot. So let's look at this in terms of a classical algorithm, but for the general picture, not just for element distinctness problems. So we consider a classical random walk algorithm where you begin from, as before, from a random vertex u that's sampled from pi. And you're going to take a step of the walk, but instead of checking right away if the sampled element is marked, you're going to repeat this 1 over delta times, where remember 1 over delta is approximately the mixing time, and then you'll check. So instead of stepping and then checking and then stepping and then checking, you're going to take a bunch of steps before you spend the time checking if your current vertex is marked. And since 1 over delta is approximately the mixing time, that means that taking 1 over delta steps of the walk is approximately giving you a sample from the stationary distribution pi. And so what we're essentially doing is we're repeatedly sampling from the stationary distribution pi and then checking if the result is marked. And if we repeat this 1 over epsilon times, then with high probability, we'll find a marked vertex. And so this is, in some ways, you could say this is a way of implementing a brute force search where the way you implement your sample is by taking 1 over delta steps of a random walk. If we sort of plug all of these values into, like, if we sort of put these all together, the cost of sampling, the cost of an update, the cost of checking, and this 1 over epsilon and 1 over delta, we can see that this classical algorithm that I've described here would have a complexity that looks like this. And as before, given such a classical algorithm, there is a quantum algorithm with a complexity where now we have square roots over both epsilon and delta. And that will also sort of find a marked vertex with high probability. So let's compare this with what we've seen so far. First, compare to brute force search. So in the classical case, if you take 1 over delta steps of the walk, then this samples from pi. So 1 over delta times u, the update, is like an upper bound on the sampling cost S. And so the classical algorithm, this classical algorithm can sort of never really do better than brute force search, because it's just, you could say it's just a way of implementing this brute force search. But that's not true in the quantum case, because now we have a square root over this 1 over delta. So in the quantum world, we can actually get an improvement. It can be that 1 over square root delta times u can actually be significantly smaller than the cost of sampling. Okay, so then let's compare the two different quantum walk options that we have at our disposal, again, using the fact that the hitting time is between 1 over epsilon and 1 over epsilon delta. So since the hitting time is at most 1 over epsilon delta, our second quantum walk framework, it can't do better than the first one in terms of the number of updates or steps of the walk needed. But it can potentially be much better in terms of the number of times we call the checking subroutine. So when checking is expensive, it may be preferable to use the second framework. And we can now see this principle in action for our example problem element distinctness. So recall our vertices are sets of x f of x pairs with edges between them. And if the sets only differ in one element and the marked vertices are those that contain half a collision pair, then we already analyzed the sampling, update, and checking subroutines. So now to analyze this algorithm in our second framework, to see that it does better, we need a lower bound on epsilon, the probability that a random vertex is marked. And in the worst case, when there's just a single collision, then we need one of its halves to be in the set of random elements. And we've already seen that this happens with probability like t over 2 to the n. And then I also claim that in this case, the mixing time is about t. And to see that intuitively, that's like, because after t steps, you've basically refreshed all t elements in the set. And so if we plug all of these values into our second quantum walk expression, this is what we get. And we find that if we set t to be 2 to the 2n over 3, then we get another optimal algorithm with complexity 2 to the 2n over 3. Okay, so then just to summarize the techniques we've seen, if we have a subroutine that samples from some distribution pi and a subroutine that checks if an object is marked, we can find the marked object in this complexity on a quantum computer where again, epsilon is the probability that a sampled element is marked. If we also have some subroutine that moves from one object to another according to some random walk p called an update subroutine, then we have two choices of quantum algorithms. One takes a number of steps proportional to the square root of the classical hitting time, but it also needs that many calls to the checking subroutine. And the other only makes a minimum number of calls to the checking subroutine, which is 1 over square root of epsilon, but potentially more calls to the update subroutine. And finally, you might also consider something intermediate between these two things, like a classical random walk where you only call the checking subroutine, say, every L steps of the walk. And so classically, what this would look like is, you get a walk P to the L, which is the walk you get where one step is to take L steps of your original walk. Then the update cost for this walk P to the L is L times the update cost for your of your original walk. And we need to look at the hitting time of this P to the L. And it turns out we can also get a quantum algorithm where we have square roots over these terms. And here, if you set L to be 1, you'll recover this framework. And if you set L to be 1 over delta, it turns out you recover this framework. So we also can get everything in between. And the precise version of this classical algorithm that is best depends, for example, on how expensive the checking cost is. If it's more expensive, you probably don't want to run it as frequently. Okay, but I'll leave the details of these to further reading. And so I want to finish by, re-emphasizing that I've glossed over many important details, but you can find these in the literature shown here. So thank you very much.
Thanks a lot for this really nice and informative and actually very pedagogical talk, Stacey. I really enjoyed it. And actually, probably the audience also enjoyed it because we have lots of questions here.
Great.
So, yeah, let's go in timely order. Maybe they are not exactly in the order of how it should come. But so, Adam Gloss asked the following question. Thank you for the very interesting question. For the presented problems, are there equivalent algorithms using continuous time quantum walks? Actually, I should mention that Adam is a great expert in continuous time quantum walks, and I have also worked with continuous time, so it's close to our hearts.
Okay, yeah, so I'm not an expert on continuous time quantum walks, so feel free to add something if I think the answer is that well, I don't believe that there are like specifically these specific frameworks looked at for continuous time quantum walks. I guess that it's probably also possible with continuous time quantum walks, because I think at least for some things there's an equivalence between continuous and discrete time. So
it's like they have maybe not looked into this up to this depth. Yes.
Yeah, maybe. Yeah. So maybe it's an interesting question if you could also do this with or how you would also do this with continuous time.
So then there are actually 3 questions from Karim Safti and longer question from Ahmed Younes and then Mansour. Let me actually maybe ask first the question of Ahmed Younes because it's a technical question. So quantum search algorithms usually assume that the superposition is complete. That is, it contains all the possible states, superposition of all possible, let's say, basis states. And few algorithms are proposed for incomplete superposition. Does the quantum random walk assume that the superposition is complete or incomplete? If you assume the superposition is complete, how do quantum random walk perform for cases when the superposition is not complete? that is some state in the superpositions are missing.
Okay, so I think you mean like kind of your initial state would be.
I think the initial state is like,
yeah.
It's not like, yeah.
Yeah, so I've sort of said it should be the quantum, a quantum state that is somehow like a coherent version of sampling from pi,
Exactly.
which is often uniform, and in the examples I mentioned is uniform. That's a nice question. So actually, these techniques also apply if you start from any other distribution on the vertices, but then you don't get necessarily a square root speed up. So then you have something here, instead of the hitting time, you have another quantity. So you have the square root of another quantity, which is not always the complexity of the classical algorithm. The classical algorithm could do better. So for example, if you start from a single vertex, S, and you have a single marked vertex, M, then what you would have this in your quantum complexities, you'd have the square root of something called the commute time from S to M, which is the number of steps it takes to get from S to M, and then the number plus the number of steps to get from M back to S. Whereas a classical algorithm would only cost the number of steps it takes to get from S to M. The classical algorithm would not care how long it takes to get back from M to S. And sometimes it's much easier to go one way than another. Like sometimes it's easy to get from S to M, but hard to get from M back to S. So that would be, so there the quantum complexity depends on both of these directions, whereas the classical wouldn't. And so then you don't get necessarily a square root speed up.
Nice, thanks a lot for this very clear answer. So let's move to the questions of, Ahmed also said, thank you very much for the answer and for the very interesting talk. And there are also other compliments here that I'm not going to read up loudly. Karim El Safti asked the following questions. One question: what would be the complexity or the depth of the circuit in terms of the problem itself? I guess if you would do like a quantum circuit of this. And then the other questions: and are there NISQ devices that could be used to implement such an algorithm? And third one is an interesting question because it brings in something very different. Finally, are there any variational forms for quantum walk? I mean, there are these variational quantum circuits. So can you combine variational quantum circuits and quantum random walks? These are, I guess, are the questions.
Okay, so I don't know about the variational, combining variational with quantum walks. I also don't, don't specifically work in that area. So maybe maybe someone else in that area could have more insight. And as for the NISQ question, I will say that this is very un-NISQ. So this is really like looking at things from a very high level and assuming everything works perfectly, and we're not looking at all at the low level circuits. And well, a couple other things that make this non-NISQ. I mean, one would be that the examples I mentioned use a lot of qubits. So like, I think all the examples I mentioned use the number of qubits that they need scales with the time that the algorithm takes. And so that's very non-NISQ. And also the fact that we're getting, at most quadratic speedups is also very non-NISQ, because probably when you factor in error correction and everything, or even constants, then you actually lose the advantage. So this is really kind of more of a long-term horizon technique. And then, there was also about depth.
Yeah, that was the first question. If you would, I guess, implement it with some gate sets. Yeah.
Okay, so then I guess like this would sort of depend on the depth of your subroutines. Like maybe there's some low depth way of preparing the initial state that you could sort of reduce this S, but then, there's nothing, you could not sort of parallelize the number of steps that you need. That's something that I think you could not sort of parallelize, at least not in general. Yeah.
I understand. So then that basically that gives the answer to this. So I think you have there is a lot of compliments here, but then there is also a question by Mansour Ziatinov. How can one prove, I guess, general lower bounds on complexity for quantum walk search? And are there some problems where the quantum walk search can't solve the problem in that optimal time that you could prove at the lower bound?
Okay, so the question about like, I guess how could you prove a lower bound in general for a quantum walk search? I guess like one way to prove a lower bound would be by some reduction. So for example, I guess like why do we know that you need to have at least 1 over square root epsilon steps, for example? Then we could say, okay, because here's how you could solve black box search like using, so we could say, here's how you solve black box search using one of these kind of quantum walk algorithms. What you do is you just have, well, you could take like a star graph. So it has a center and a bunch of edges coming out of it. And each edge coming out, each has a vertex representing one of the possible solutions. And if you random walk on this, you're basically just checking something at random and then going back and then trying another one at random, checking, going back, trying another one at random, checking and going back. And since we have lower bounds on black box search, we know that in general, these quantum walk algorithms can't do better than that lower bound. So that's one way. So by reduction is one way we can prove kind of lower bounds for this general picture. What was the other part of the question? And
are there any cases where it's not known? Let me read the problem. Are there some problems where quantum walk search cannot solve it in optimal time? I guess optimal, like what, like in lower bound optimal time? Yeah.
Yeah. Okay. So I mean, so I guess, okay, there's some problems like where the best quantum algorithm is not using quantum walk search. So for example, for factoring, I don't know how you'd get a quantum walk algorithm that, well, okay, and the example, the ones that I showed anyway, only get a quadratic speed up. So we probably can't get an optimal factoring algorithm, but there are also like maybe some problems where we don't know. So one example is triangle finding. This is like kind of a long open problem in quantum query complexity, where I believe the best currently known quantum algorithm does use quantum walk search. And this problem, by the way, it's you're given a graph as input, and you want to know, does the graph have a triangle, or is it, or is there no triangle in the graph? Where a triangle is just like what it sounds like. It's like a cycle of 3 edges. And so for this problem, there's still a gap between the best known lower bound and the best known upper bound. And so it's possible that this could be improved, maybe using quantum walks or maybe using some other technique.
Thanks a lot. And you really got a lot of compliments. There are also one new question popping up, but actually as one of the co-organizers wrote that everyone is also welcome to post questions on the Discord and continue the discussion there. I think so it would be great. Thank you very much. Okay, so let's stop the recording.